This is problem number 5 from the optimization homework. So this one is dealing with a rectangular solid, right? So a rectangular solid is really just a box, right? A three-dimensional box. So find the dimensions of a rectangular solid with a square base with maximum volume if its surface area is 337.5 square centimeters. All right. So as with the other ones we had done, we're going to have a constraint, or constraints plural, and then we're going to have a function to optimize. And again here we're finding a maximum, right? We want the maximum volume, so we're maximizing. All right, so the constraint in this case is the fact that the surface area has to be 337.5 square centimeters. Now, a box, right, a rectangular solid, a box would look something like this. Where you'd have your dimensions, length, width, and height, right? So in general, the surface area of a box is going to be a top and bottom. So there's 2 length times width, right? Then 2 sides, which are each WH. So 2 WH, and then a front and back, which is this and that back piece. So those are LH, so 2 LH. And in this case, they tell us the surface area is 337.5. So our constraint is actually going to be 337.5 equals 2LW plus 2WH plus 2LH. That's our constraint, right? But now luckily in this case, because see the problem here is you have 1, 2, 3 variables, L, W, and H. But the saving grace here is that they tell us that this thing has a square base, meaning this down here and this up here are squares, which means that L equals W. So if we put these two constraints together, now we can replace W with L or L with W. I'll replace W with L, and we can combine these two constraints into one constraint that just looks like 337.5 equals, that W is now an L, so it's 2L squared. This W is now an L, so this is 2LH, and then this is still 2LH. So these two 2LHs are like terms, so they'll become 4LH. So we'll really have 2L squared plus 4LH. So that's our one constraint now. All right. And now the function that we're going to optimize, of course, we're trying to find the maximum volume, right? And of course, the formula for the volume of a box is really LWH. Okay, so now we've identified what we're trying to maximize, which is this volume formula, and we have our constraint equation here. So now what we finally have to do is solve this constraint equation for one of the variables, and then take that expression and plug it in to our function that we're trying to maximize. Alright, so now we've got our constraint and our function to optimize. Now what we need to do here, of course, is solve this constraint equation for a variable. And the one we're going to choose is h because it's going to be easier to solve for. So how would we isolate this h? We get rid of this 2l squared by subtracting. And then we're going to divide by 4l, right? So we'd have 337.5 minus 2l squared equals 4lh. And then we would divide both sides by 4l. to isolate the h. So then we're going to have h equals 337.5 minus 2l squared over 4l. And that's what we had to do because, again, the problem with the function that we were going to optimize is that it had 3 variables in it. So now what we're going to do is we're going to take this expression for h and put it right there. And because we also know that w equals L, we're going to take the L and plug it in there for w, and then all 3 of those dimensions are now going to be in terms of L. So now I can rewrite my volume formula as V equals L times L times that expression that we had there and what happens in this now this function we have here is these L's will cancel, so I can just write this as L times 337.5 minus 2L squared all over 4. And now the issue with this is not a quadratic function, right? If I distributed this L, this would be a cubic function, right? It'd be 337.5L minus 2L cubed over 4, which is cubic, which we don't have a formula for finding the maximum. Now in calculus, you learn how to do that. You learn how to, find the maximum point. But here we have no alternative but to take this function and enter into the calculator. So I've already done this. So if I go to my y1, you can see I've entered it as x times 337.5 minus 2x squared over 4. Now what I want to do is set a window. So if I go to my table, I can see that this is a length we're dealing with here. So we're never going to deal with negatives. So you can see that at 0, it's 0. It increases to about here, then it starts going back down, and by 13 it's negative. So if we use our window from 0 to 12 for x, and make y go from 0 to 450, let's say, to be safe, because 419.13 is the maximum here. Set your window like that, 0 to 12 and 0 to 450. Graph it. There it is graphed. Now you can see we have a maximum point right here, which we're going to find by doing our calc maximum. And when we do this, left bound, right bound, guess, and we get 7.50000015, which is 7.5. So I'm going to say the length is 7.5, and this is measured in centimeters. Now we know the width is also 7.5 centimeters because they're equal. And now the height was just this expression here, 337.5 minus 2L squared over 4L. So we can get the height then by just doing 337.5 minus 2 times 7.5 squared, and divide this by 4 times 7.5, right? In parentheses, 4 times 7.5. And we get